Imagine for a moment you could travel through a black hole, and instead of being crushed by infinite gravity, you emerged on the other side of the universe through something completely opposite, a white hole. An object so strange and fascinating that it expels matter and energy with the same intensity a black hole devours them. Sounds like science fiction, doesn't it? But the mathematics of the universe suggests these objects might be as real as the stars we see in the night sky. Today, we're diving into one of the most intriguing concepts in modern physics, white holes. We'll discover how they were born from the same equations that predicted black holes, explore if they could actually exist in our universe, and investigate their possible connection to mysterious wormholes. Get ready for a journey that will challenge everything you think you know about space and time. Hello, cosmic explorers. Welcome back to Cosmic Frontiers, where we transform the universe's deepest mysteries into adventures of discovery. We're building an incredible community of curious minds on our journey towards 1,000 subscribers, and each one of you makes this exploration even more special. To understand what a white hole is, we first need to revisit its more famous cousin, the black hole. Imagine a black hole as a gigantic cosmic drain. Everything that approaches it is inevitably sucked in, including light itself. That's why we call it black. No light escapes from there to reach our eyes. Now, imagine the exact opposite. Instead of sucking everything in, this mysterious object expels matter and energy outwards with tremendous force. Nothing can enter it, only exit. That's the fundamental concept of a white hole. The story of white holes begins in 1916, when German physicist Karl Schwarzschild was solving Einstein's field equations. Schwarzschild was in World War I when he made this revolutionary discovery, unfortunately dying shortly after from an illness contracted on the front. But his mathematical legacy would forever change our understanding of the universe. When Schwarzschild analyzed Einstein's equations, he found two possible solutions. One described what we now know as black holes, regions where gravity is so intense that nothing can escape. But there was a second solution, a mathematical mirror image, regions where nothing could enter, only exit. These were white holes, although the term was only coined decades later. Think of it like a cosmic coin. On one side, we have the black hole, which devours everything. On the other side, we have the white hole, which rejects everything. Both are valid solutions to the same fundamental equations that describe how gravity works in the universe. It's like discovering that the same mathematical formula explaining how water goes down a drain also explains how it could gush out with infinite force. But here arises a fascinating question. If mathematics allows for both, why do we see black holes throughout the universe, but have never observed a white hole? The answer lies in a fundamental concept of physics, the arrow of time. Imagine watching a movie in reverse. You'd see strange things, broken eggs reconstituting, smoke returning into a chimney, people walking backward. A white hole is essentially a black hole running backward in time. While a black hole represents the final destiny of a massive star that collapses, a white hole would be like watching that collapse happen in reverse, a cosmic explosion that creates matter instead of destroying it. Here's where physics becomes truly mind-expanding. In Einstein's general relativity, time is not a universal straight line, but rather a dimension that can be curved and distorted by gravity. In theory, Einstein's equations are time-symmetric. They work equally well whether time runs forward or backward. But our universe has a clear preference for the direction of time, always from the past to the future. To visualize this, imagine a perfectly calm swimming pool. If you throw a stone into the water, it will create ripples that spread outwards. We never see the opposite happen naturally. Waves converging perfectly from all directions to form a stone that jumps out of the water. Technically, the laws of physics would allow this, but the necessary initial conditions would be so precise that they are practically impossible to occur naturally. Similarly, a white hole would require such specific and improbable initial conditions that most physicists consider its natural existence extremely doubtful. It would be like trying to make all the air molecules in a room move in the exact direction to form a perfect hurricane. Mathematically possible, but practically impossible. However, some scientists have proposed scenarios where white holes could exist. One of the most intriguing ideas is that they could have formed in the first moments after the Big Bang, when the universe's conditions were so extreme and chaotic that even the most improbable configurations could have materialized. Imagine the primordial universe as a boiling cosmic soup, where the laws of physics we know today were just beginning to establish themselves. In that environment of unimaginable energy and density, perhaps some white holes were born along with spacetime itself. If that happened, they would be incredibly ancient relics, silent witnesses to the first instance of creation. But here arises another fascinating question. How could we recognize a white hole if we found one? Unlike black holes, which are invisible because they don't emit light, a white hole would be extremely bright. It would be constantly expelling matter and energy, creating a cosmic spectacle of epic proportions. Some scientists have speculated that certain mysterious astronomical phenomena could be evidence of white holes. Gamma ray bursts, for example, are the most energetic events known in the universe, releasing more energy in seconds than our sun will produce in its entire lifetime. Could one of these explosions be the signature of a white hole releasing its accumulated energy? It's a tempting possibility, but we still lack conclusive evidence. Now, let's explore one of the most exciting connections in theoretical physics, the relationship between white holes and wormholes. To understand this, we need to expand our cosmic imagination even further. Imagine spacetime as a sheet of paper. A black hole would be like a funnel that punctures this sheet, creating a deep gravitational well. Now, imagine that this funnel connects to another funnel on the opposite side of the sheet. This second funnel would be a white hole. The connection between them would be what we call a wormhole or an Einstein-Rosen bridge. This idea emerged from the work of Einstein and his colleague Nathan Rosen. In 1935, they realized that the equations of general relativity allowed for the existence of bridges in spacetime, connecting distant regions of the universe, or even different universes. It's as if you could enter through one door in Sao Paulo and exit through another in Tokyo, without traversing the distance between them. In this scenario, a wormhole would literally be composed of two components, a black hole at one end and a white hole at the other. Anything that fell into the black hole would instantly emerge from the white hole, potentially in a completely different region of space and time. Think of it as the ultimate cosmic transportation system. Instead of traveling through normal space, which would take millions or billions of years even at the speed of light, you could use a wormhole to instantly cross galactic distances. It's every science fiction writer's dream made mathematically plausible. But, as always in physics, reality is more complicated than fantasy. Even if wormholes can exist mathematically, keeping them open and stable would be a monumental challenge. Most theoretical models suggest they would collapse instantly, closing before anything could pass through them. To keep a wormhole open, we would need something called exotic matter, a type of matter with repulsive gravitational properties, the opposite of normal matter. This exotic matter would have negative energy density, something we have never directly observed in nature. It would be like trying to keep a soap bubble stable using air that weighs less than nothing. Theoretically possible, but practically challenging. Some physicists have speculated that extremely advanced civilizations might be capable of creating and maintaining artificial wormholes. Imagine technology so sophisticated that it could manipulate the very fabric of spacetime, creating cosmic shortcuts on demand. It would be the equivalent of having total control over the geometry of the universe. But even if we could create wormholes, they would present fascinating paradoxes related to time travel. If a wormhole connected, not just to points in space, but also to moments in time, it could theoretically allow travel to the past. This would create the famous temporal paradoxes that so intrigued physicists and philosophers. Imagine you traveled through a wormhole to the past and met your grandparents before your parents were born. If you prevented your grandparents from meeting, how could you have been born to make the time travel in the first place? This is the kind of logical puzzle that arises when we play with the extreme possibilities of theoretical physics. Currently, our search for white holes and wormholes continues both on paper and in space. Theoretical physicists are constantly refining mathematical models, exploring under what conditions these objects could exist and how we might detect them. Meanwhile, astronomers scanned the sky looking for observational signatures that could indicate their presence. One of the most promising approaches is to look for violations of causality, events that seem to happen without apparent cause or in a strange temporal order. If a white hole were expelling matter into our universe, that matter would appear out of nowhere, violating our normal understanding of cause and effect. Another intriguing possibility is that some of the most energetic phenomena in the universe, such as quasars or supernova explosions, could have white hole components. Perhaps what we interpret as conventional astrophysical processes are actually manifestations of these exotic objects. Technology is also evolving to help us in this search. Gravitational wave detectors like LIGO have already revolutionized our ability to listen to violent cosmic events. If white holes existed and were active, they would likely produce gravitational waves with unique signatures that we could detect. Imagine the moment we could capture the gravitational sound of a white hole expelling matter into the universe. It would be like hearing the universe cough, releasing something that was trapped in its most intimate depths. This moment would represent not only a scientific discovery, but a fundamental expansion of our understanding of reality. Even if we never find direct evidence of white holes, they remain valuable as conceptual tools. They force us to question our assumptions about time, causality, and the fundamental nature of space-time. They are like thought experiments that expand the limits of our scientific imagination. Furthermore, the study of white holes has profound implications for our understanding of the universe's origin. Some cosmologists have proposed that the Big Bang itself could have been a type of white hole, an event where all the matter and energy of the universe were expelled from a primordial singularity. From this perspective, each of us would be made of matter that one day emerged from a primordial cosmic white hole. Our atoms, forged in stellar furnaces, would have their ultimate origin in that moment of explosive creation. It's an idea that connects our individual existence to the most fundamental structure of the cosmos. Recapping our cosmic journey today, we discovered that white holes are valid mathematical solutions to Einstein's equations, theoretical objects that expel matter and energy instead of absorbing them. We explored how they could be connected to wormholes, creating bridges through space-time that challenge our normal understanding of reality. And we saw how, even if we never find them, they continue to expand our imagination about the possibilities of the universe. The search for white holes reminds us that the universe still holds deep secrets, waiting to be discovered. Every equation we solve, every observation we make, every theory we develop brings us a little closer to understanding the true nature of cosmic reality. This leads us to a profound reflection. If white holes truly exist somewhere in the cosmos, they represent a form of continuous creation, points where the universe is constantly being reborn. In a cosmos dominated by entropy and the tendency towards disorder, white holes would be oases of pure creation, reminding us that the universe still has surprises to offer. Cosmic explorers, which aspect of white holes most piqued your curiosity? Do you think we will someday find evidence of these mysterious objects, or will they remain forever in the realm of pure theory? Share your thoughts in the comments. I love reading your reflections and theories about the universe's mysteries. And since we're talking about cosmic mysteries, what enigma of the universe would you like me to talk about in the next video? Dark energy, multiple universes, the nature of time. Leave your suggestions in the comments. You are the ones who guide our journey of exploration. We are on an incredible adventure towards 1,000 cosmic explorers, and each one of you makes this community richer and more curious. If this video expanded your horizons on the possibilities of the universe, join our crew by clicking subscribe. Together, we will continue to explore the frontiers of cosmic knowledge. Like this video if it sparked your imagination about the mysteries of space-time, and share it with someone who is also fascinated by the infinite possibilities of the cosmos. In the next video, we will explore another enigma that challenges our understanding of reality. Stay tuned. Until our next cosmic adventure, keep looking at the stars and questioning the mysteries of the universe. The cosmos is full of wonders waiting to be discovered, and each one of you is part of this extraordinary journey of knowledge.